This is an AX mechanics question on variable acceleration. A particle P moves along the x-axis. At time t seconds, where t is greater than or equal to 0, the displacement x meters of P from the origin O is given by x is equal to half t squared times by t squared minus 2t plus 1. Part A, find the times when P is instantaneously at rest. So the first thing to note is that when something is instantaneously at rest, it means that its velocity is equal to 0. So we need to find that velocity, which means differentiating the displacement function. That means finding dx dt. Before I do that, I'm just going to expand these brackets, just make it a little bit easier to differentiate. So x is going to equal to half t to the power 4 and then minus t cubed and then plus half t squared. So v is going to be dx dt. So let's differentiate and see what we get. So v will be equal to 2t cubed minus 3t squared and then plus t. Now remember, we want to find when v is 0. So what we're going to do is that we set this equal to 0. Now I want to factorize this to find its roots. Since every term has got a t in it, I'm going to take t out. So I'll have v is equal to t, and then in brackets 2t squared minus 3t plus 1. That makes the bit in the brackets here, the quadratic, a little bit easier to factorize. So v is equal to t. So now I'm going to factorize the quadratic. Now since I've got 2t squared, that means I must have 2t in one bracket and t in the other. I need to get 1, which means that actually I need to have 1 at the end of both brackets. It's just where I put the plus and the minus signs. Now I want negative 3t. So if I put a negative here, that will give me negative 2t, and a negative here, that will give me a negative 3t, and then multiply together, that will give me the plus 1. So from this, I can work out what the roots of v are. So v is going to be 0 for these following values of t. First of all, when t is equal to 0, let's just mark it out. So here t is equal to 0. Also, when 2t minus 1 is equal to 0, that means when 2t is equal to 1, or t is equal to a half. And from here, this will be when t minus 1 is equal to 0. In other words, when t is equal to 1. So the times when P is instantaneously at rest will be when t is equal to 0, when t is equal to a half, and when t is equal to 1. Part B, find the total distance travelled by P in a time interval for t greater than or equal to 0 and less than or equal to 2. So let's try and understand what's going on with the path of P. So at t equals 0, it's moving in a certain direction. And then when t equals a half, this is when v equals 0. So I'm just going to assume that it changes direction. It may or may not, but it could be changed direction. And then when t equals 1, its velocity becomes 0. It could be changing direction again. And we're only interested in up to the point where t equals 2. Now, because it could be changed in direction, we need to work out each one of these distances separately and add them together. So we need to work out what the distance is from t is 1 to a half, then from a half to 1, and then from 1 to 2, and those three we need to add together. If we just did 0 and 2, or we just put 2 in for x, we would not get the total distance it's moved. We would just get basically its finishing position when t is 2. So let's find its position at these different times. So let's start with t is equal to 0 and find out what its position is. That means we just put 0 into this. So if we do that, that will be a half times 0 squared, and in brackets 0 squared minus 2 times 0 plus 1. Now anything times by 0 is 0, so its position is 0. Okay, so at this point its position is 0. Now let's work out its position when t is equal to a half. This is the next time when v is equal to 0. So x is going to equal to half times by a half squared. That's like t squared. And then in brackets a half squared again minus 2 times a half plus 1. And that will give us 1 over 32. So when t is a half, x is 1 over 32. So I know that in this part of the journey, the yellow part, it's travelled a distance of 1 over 32. We're now going to work out where its position is when t equals 1. Okay, that's at this point here. So that will give us x is equal to a half times by 1 squared times by 1 squared minus 2 times 1 plus 1. And that gives us an x position of 0. So basically what's happened, it has moved back to basically its starting position. So this diagram here, don't take it literally, it's just to give us an idea of what's going on. So that means that in this blue part of the journey, it's moved another distance of 1 over 32. So maybe down here I should keep a tally of the total distances. So I've got 1 over 32 so far for the blue part, yellow part, another 1 over 32 for the blue part, and now I want to work out what the yellow part is, and to do that I will need to make t equal to 2 right at the end and work out what its position is. So the x position is going to be a half times by 2 squared. Let's just get this out of the way and put the 1 over 32 here out of the way, times by 2 squared minus 2 times 2 plus 1, and that gives us 2. So right at the end the x position is 2. So that means that this green part of the journey is a distance of 2. So we've got 1 over 32, another 1 over 32, and then another displacement here of 2. So that will give us the total displacement, which is 2 and 1 over 16 meters. And lastly, part C, show that P will never move along the negative x-axis. So we basically need to show that this can never be negative. Now let's factorize it, because often factorizing can help us see what's going on, or maybe completing the square. Now in the brackets here, I've got t squared minus 2t plus 1. That actually factorizes to t minus 1 all squared. Now this statement here that I've written can never be negative, because I've got a square here. Whenever you square anything it's positive, and t is squared here. So basically this means that x can never be negative, so it's always greater than or equal to 0. Therefore x will never move along the negative x-axis. So that's because of this statement here leading to this statement. And while I'm at it, I might as well highlight my previous answers from part A.